So welcome to today's Meow seminar with Arkadev Chattopadhyay, who will start, and Sreejata Bhattacharya, apologies for mangling all the names, who will tell us about exponential lower bounds for ResLin proofs of nearly quadratic depth. So please, Arkadev, who will start, take it away.
Oh, I did something that, okay, can you see my slides?
I can see your slides well, yes.
Okay, thank you. Thank you, Jakob. Thank you for the invitation to talk here. And it's always great to be among friends. Okay, so I must say, as I said, the plan is I will talk until a while, and then at some point we'll decide to switch. We can take a break. So the breaking point will also be a little bit, online, depending on how we go. Okay, and stop me whenever you have any questions. I'm more than happy to answer that. And I must warn you, proof complexity is a very, very new thing for me. So I'm here to learn from you. If you have any questions, please don't keep them to yourselves. Just share it with me. Thank you. Okay, so here we go. So this is joint work with Sreejata Bhattacharya, who's a student at TIFR here. So here's Cook's program towards proving NP different from co-NP. This you all know very well, but let me just remind you, if NP were equal to co-NP, then there exists a propositional proof system in which all true statements will have essentially very efficient small proofs. So one way to disprove that is to show super-polynomial lower bounds on proofs in stronger and stronger propositional proof systems. Just as in circuits, we deal with stronger and stronger circuit classes in the hopes of making progress towards P different from NP. So the program is sort of, from what I understand, pretty parallel here, except as you will see that we make less progress here than what we have been able to do in circuit complexity in some sense. Okay, and here's the slide. I won't show all the proof complexity classes because that'll take us on a tangent. So the important proof complexity classes here is resolution, which is a very important and simple, elegant proof system, which all of you know. I'll just define it again. And then this proof system is polynomially simulatable by bounded depth Frege, which I'll call AC0 Frege. And this box here is meant to say that we have lower bounds for these two proof systems. Not that, I mean, from what I understand, research is pretty ongoing in each of them, but we still understand a lot of things about it. Particularly, we can prove quite strong lower bounds. And then when we go to AC0 mod 2 Frege, so this is where each proof line is a bounded depth circuit, but with additional parity primitives. We certainly go out of the domain from where we, or the range where we have proof, where we have low bounds, to territory where we don't know much at all. So this is a major open problem in proof complexity to prove lower bounds for AC02 Frege. And this has been open for a really long time. So back in 2014, there was this very nice paper by Itsykson and Sokolov, which introduced this smaller natural fragment of AC02 Frege, and a certain generalization of resolution, where we add to resolution. In resolution, you deal with ordinary clauses. Every line is an ordinary clause. In res with parity, which I'll sometimes call res parity or ResLin interchangeably here. Here we allow, as we will soon see, more general clauses, linear clauses. Okay, and I'll make sure I'll tell you what I mean by that in a moment. So it's some natural generalization of resolution with parity. Okay, that's what is ResLin, and it is certainly sitting between AC02 and resolution. And what turns out is, as they observed, that there are no known lower bounds even for this intermediate proof system that we are calling ResLin. Okay, so that was a bit surprising that just a little perturbation of resolution by adding parity already throws us off. And what I'm going to tell you today is that there has been some exciting recent progress after this paper by Itsykson and Sokolov. It started a really interesting train of papers, and I myself got very interested in this proof complexity by looking at the Itsykson and Sokolov paper. So this work that I'm going to talk about will continue and very much build upon the exciting recent progress, and I would like to share this with you. Okay, so let me just now give you a quick recap of what resolution is and how ResLin augments resolution. So on the left, you have resolution, where there are essentially two main rules of inferences, which is if you have an ordinary clause A or X, you start with these two clauses A or X and B or not X, then you can resolve on this variable X and not X can be resolved to give you A or B, right? And this is the resolution main inference. And you have another thing which looks like a very innocent thing called the weakening, where you start with a clause A and you are allowed to add A or X. And obviously it's a weakening of A, and that's why it's called weakening. So that's resolution. On the right side, let's look at that. Let's look on the right side. So now you have A, B. These are linear clauses, linear over F2. Okay. So these clauses would look as an OR of a bunch of parities, like A might look as a bunch of linear equations like L1 is equal to 0, L2 equal to 1, and so on. And now if you have such a linear clause A or this additional equation L equals 1 and B or L equals 0, just as over here on the left, you can resolve on this L and generate the clause A or B. So this is the analog of the resolution rule in ResLin. Okay. And further, you have the weakening rule, where the weakening rule I have written in the following way, where if I start with A, then I can add another linear equation to it and produce a fatter clause, A or L equals 0 or L equals 1. And I must say here, there's a very important thing here, which is going to come up in the next slide, which is that even though I wrote it here A, I can express, because now I have the system of linear equations, I can express A in another basis. Okay, so sometimes weakening also refers to when you don't add this L is nothing, you don't add this, but you just rewrite A in a different basis and express it differently. So if you think of it, the negation of A is an affine space, just as the negation of a clause in resolution would be a Q. There is the negation of a clause, a linear clause would be an affine space. And because it's an affine space, you can express it in many different bases and many different ways. And this is, as my next slide is going to show, that this is the root cause of all problems in understanding resolution over parities. Okay, because in standard resolution, there's only one basis, standard basis, so it's easy. It's very localized. We understand it much better. If you've dealt with AC0 with parity circuits, exactly the same kind of problems show up there. And so, here things are nice. You have one basis, whereas here you can do a change of basis, and there is a multitude of bases, and depending on which one is convenient, you choose one, and that causes a lot of problems. And it also causes resolution with parities to have its own power. So let me just give you a quick example of resolution with parity in action. So suppose I have this triangle, a graph. There are three vertices, and the edges are the variables. Okay, so x1, x2, x3, there are three variables. And I have these three equations, linear equations, which are constraints, which are obviously unsatisfiable, because if you sum up all of them, you get 0 on the left-hand side, whereas you get 1. This summing up is all over F2. Okay, so this system is therefore unsatisfiable, and this naturally gives rise to a system of clauses, ordinary clauses. I've just from the truth table I've constructed these, and so this becomes when represented in this way, this is a CNF formula that is just not satisfiable. Okay, and here's a way to show to see how you can construct a ResLin proof of this. Well, let me do the dual view first. It's often going to be very useful, which is just as in the case of resolution, the dual view is of a decision tree or a decision DAG, an ordinary decision tree or an ordinary decision DAG. In the case of ResLin, if I'm looking at a tree-like proof, then it would be a parity decision tree searching for the falsified clause. So given an assignment, this parity decision tree is looking for a clause that's falsified because the formula is a contradiction. There has to be one, and it's searching for that. And otherwise, for a general ResLin proof, it will be a linear DAG, and which we will come to very soon. But let me just explain you. So if you just look at this, so if you sum these two things up, the first two things, you get x1, x2 plus x3. So that's why all of these three things sum up to on the left to 0. So I'm sort of trying to mimic in this little example binary search. So I just first query what happens to x2 plus x3. This is a linear query because I'm allowed to do that because it's a parity decision tree. And now there are two ways to go, 0 or 1. And then going one of these ways, I query x2 because x2 plus x3 is 0. So I know that this particular linear equation was unsatisfied. And I further probe x2 and I find out which one of them. And therefore, I can point out the corresponding clause which gets falsified. And I do the same over here. Now, the nice thing is, for those who haven't seen this before, is that given this, I can build a resolution with parity proof out of this. Notice that I can rewrite these things as linear equations, as linear clauses by saying x2 equals 1 or x3 equals 1. Just x2 or x3, I'm rewriting it, no change so far. But now I can do, as I was saying, I can do a basis change. Suddenly I do this basis change, and now you get x2 plus x3 equals 1 or x2 equals 1. And these two are completely equivalent. It's just I've done a basis change, which was not there for me in resolution, but now I have access to it. And I likewise do a basis change. Now with this, armed with this basis change, now I can resolve, let's say on the left-hand side, so I can resolve this x2 equals 1 and x2 equals 0 and go and derive x2 plus x3 equals 1. Okay, similarly, I can do the derivations on the right-hand side. You can verify that. Just notice now an interesting thing will happen in the sense that, well, I've derived x1 plus x3 equals 1 and x1 plus x2 equals 1, and I seem at this point I can't, resolve on these two because there's none to resolve. But now I will do this weakening trick. So I weaken it with x1 plus x2 equals 0, and then I do a basis change. And once I do a basis change, I get x2 plus x3 equals 0 or x1 plus x2 equals 0. Okay. And now you can see that this thingy, and on the left-hand side, this one, now I can resolve on x1 plus x2 equals on x1 plus x2. This one here wants it to be 1, and this one here wants it to be 0. So I can do that, and I can derive x2 plus x3 equals 0. Okay. So, and then we are good to go back again. And now we derive the empty clause, which obviously proves that this system was unsatisfiable. So that's an example of resolution with parity in action, where I just showed you that at least for a tree-like system, it's important to be able to, add, weaken, and and then do a basis change. It turns out in a DAG as well, the change of basis is an important ingredient. Okay. All right. So I hope you got that. So the point is,
question, just a technical question. On the left, I mean, once you have that x2 plus x3 is 0, you already have a violated constraint, but I still have to continue and ask for x2. I mean, what's the... So do I need to know all the variables in the violated constraint and not just that the constraint itself is violated, or this is just not an important point?
No, on the left here, what I wanted to do was, although I know that this equation has been violated, I'm trying
Yeah.
to hone in onto this one of these clauses because I always begin
Okay.
with this clause.
Okay. Okay. So you're looking for the okay. Sorry. Yes. Got it.
Yes, because I'm just treating resolution with parity as just as a proof system that works with CNF.
Yes. Yes. Okay. I get it.
All right. Okay. So let's move on. Any further question? Okay. So, well, what I showed you here is an example of a Tseitin formula where you're given a particular graph, okay? And for associated with each vertex of the graph, we have a charging function, yeah, which just assigns the vertex to 0 or 1. And then this naturally sets up a system of parity constraints. Well, I look for every vertex, you get a parity constraint which just sums up. So the edges of this graph, just as before, are the variables. So you want to sum up all the edges incident to a vertex, and that should be equal to whatever that vertex was assigned to, modulo 2. Okay, this whole sum is modulo 2 or over F2. Okay, and this we do for every V in the vertex. So that gives rise to a parity constraint. And now a simple fact, which was the case before, is if the sum of these charges is 1 mod 2, then there's obviously a problem, because if you sum up the left-hand side, all the variables are going to cancel because every edge occurs exactly in 2 constraints. So you get 0 equals 1. So this therefore is a proof that this constraint, when under this additional condition, is never going to be satisfied. It's unsatisfiable. And from now on, I will always look at graphs that I start with where all the FBs are 1 and I have an odd number of vertices. That ensures that this constraint is satisfied to begin with, and therefore such a system of constraint will be unsatisfiable. Okay. And again, if this, if the degree of these edges, if the degree of this graph is small, like a constant or even order log n, each of these constraints you can convert into a formula with the blow up the number of clauses being, well, just polynomial in n, where n is the number of vertices. Okay. So the formula, the CNF formula that asserts the satisfiability of this constraint is what I will call phi. Sometimes I'll write a subscript of G, because G is the graph from which this formula arose. And the variables of this is nd by 2, where d is the degree of the graph. And in a typical setting, or for a while, I'll assume that d is order log n. So it's a log n degree graph. So, the total number of variables is about n, just a little bit more. And the total number of clauses is therefore polynomial in n, where n is the number of vertices. Okay. So my graphs will always be d-regular. They will be regular graphs. I won't assume non-regular graphs. So given a graph, I get such a formula. And these are called Tseitin formulas. This was introduced by Tseitin. The Tseitin formulas make a huge difference between resolution, the power of resolution, and resolution with parities, because Urquhart in 1987 showed that if you take a degree 3 expander of odd size, then the resolution proof, the size of a resolution proof, is always going to be exponential. Okay. I mean, technically speaking, he used a bipartite expander, but that was not needed. So I'm just stating it in a more general way. So therefore, these graphs, when they are expanders, the Tseitin formulas that you get out of them are pretty damn hard for ordinary resolution. But based on just what we saw, I'm going to appeal to the proof by picture that I showed you. These formulas turn out to be quite simple for resolution with parities, even for tree-like proofs. In fact, we saw that, right? You can do binary search, which is what I was doing, and you can show that, it's just polynomial. So the depth of this search tree would be about order log n, and therefore the size would be polynomial. So even tree size is just polynomial. Okay. And that's not surprising because, well, we added the power of parities. This formula seems to be hard because you have to sort of track parities, and that seemed quite hard for ordinary resolution, but resolution with parities can very easily do that. Yeah, I consider it like the analog of, if I look at AC0 with parity circuits, the first thing that it can do beyond what AC0 can do is counting mod 2. This is exactly what's going on here. Okay, in the proof complexity world. But it just shows that we are dealing with something that's more powerful than resolution. Okay, so let me just now look at, as I've been talking about, I've been always comparing with circuit complexity. Yeah, let's compare what we know in the circuit complexity land. Well, in circuit complexity, we know this classic work of Rasborov, 87. 87 is a very interesting year for computational complexity. Barrington's theorem was also proved, I think, in 87. Rasborov's famous paper came out in 87, and we just saw Urquhart published his paper also in 87. There are many other interesting things that happened that year. Anyway, so AC0 with parity circuits, they need exponential size to compute majority. This was proved by Rasborov, and he used his method of approximations, which he had just invented to show his famous monotone lower bound. He used also for bounded depth circuits with mod gates, and he could prove this result. Okay, and one may wonder that why can't we adapt this technique? That seems pretty powerful. Not just it can deal with any bounded depth circuits with mod gates sprinkled in anywhere. Well, that's been a challenge I assume all proof complexity theorists have been grappling with. We don't know how to use approximations in proof complexity. What's an approximate proof? That's an interesting question. Okay, so we don't know how to adapt Rasborov's approximation technique, and therefore we have not been able to make use of Rasborov's method for dealing with AC0 mod 2 Frege. So what we are going to do is we're going to borrow another technique called lifting that originated or that made solved many problems in communication complexity, and see whether we can use those techniques to make progress here. Yeah, that will be the bulk of my talk. And if something is clear, please let me know. Okay, so lifting with gadgets. Yeah, so as I said, this originated in communication complexity, has had many applications. I must say, sorry, I wanted to add this thing. I'm not a proof complexity person, so I learned this pretty late. Although I suspect Jakob may have told me earlier. Actually, there is an old paper of Urquhart which does lifting in proof complexity, where he lifts with a 2-bit gadget called XOR. Okay, but that lifting lifts resolution width to resolution proof size. Okay, and it's a very useful thing. I mean, we know that thanks to Ben Sasson and Wigderson, we know now that this is not needed, but it just shows up in many different situations as of immense help. So I'm sorry for not crediting here Urquhart on my slide. As I was making my slides yesterday, I realized a little late in the game that I missed crediting Urquhart. So but as you will see in communication complexity, we have had a way more sophisticated lifting with gadgets, and that's what we are going to talk about here. Okay, so in proof complexity, sophisticated lifting with gadgets from what I know happened for the first time in this very beautiful paper from 2018 by Gerg, Gus, Kamat, and Sokolov, who showed that the resolution width with suitable gadgets can be lifted to cutting planes size. So here you see, this is the kind of lifting I'm talking about, where you start on the left from a weaker proof system like resolution, and on the right, after lifting, you're able to say things about a much stronger proof system, like cutting planes. Yeah. And inspired by that, you would like to say, well, shouldn't we have a lifting technique that takes resolution width or size ordinary resolution with the size and lifts it to a stronger proof system like resolution with parity size. Yeah. So we're still in search for such a technique. We don't have it. Okay. But there has been some progress. So in 2023, two independent works, Beam and Korot, and in a joint work with Mande, Sanyal, and Sherif, we proved a lifting theorem, but it's a limited lifting theorem. We start on the left-hand side with a tree resolution. So we're talking about tree resolution depth. Yeah. So the proofs on the left are tree-like. We take the depth of such a proof, lift it with a certain gadget, and we can now prove a resolution with parity tree-like proof size lower bound. So if the proof here had depth d, then the size of the lifted formula will have proof size exponential in d. Okay, and this later work introduced a certain kind of gadget called stifling gadget. Yeah, so these are gadgets of constant size, like majority with 3 bits, inner product on 4 bits, and so on. And I can explain this gadget very easily. It's a very simple gadget. So let me explain by majority. So this is majority with 3 bits. And notice that this red colored bit is what I'm stifling to. So no matter how, once I fix these 2 other yellow bits to 0, this bit gets stifled, meaning the function, the gadget gets fixed to 0. Yeah, because the majority is obviously going to be 0. And likewise, I can stifle this bit to 1. Yeah. So that's what a stifling gadget does. Technically, it's called a one stifling gadget. You give me a bit, I can stifle it to whatever value you want, whatever value of the function you want, by assigning properly the remaining variables. Okay. So a random gadget will have this. So a large number of gadgets have this property. And what we found out is that the stifling is very useful in lifting resolution, tree-like resolution depth to tree-like res parity size. Okay. And this implies a host of lower bounds. This gave us a systematic way. So, every time you have a lower bound on tree resolution depth, you can lift it to a tree res parity size. In particular, now if you give me a Tseitin formula on an expander graph, yeah, and you lift with just a 3-bit majority, then this whole thing, this combination shows us the tree-like size for even resolution with parity is now exponential. Yeah, so if you just lift with a majority gadget, the complexity becomes very large. Okay, so let's now go from tree-like. I'm going to now trace the recent developments that lead us to our result. So tree-like we were able to do in a systematic way using lifting. Now, the next target going by what happened to resolution would be a regular resolution. So regular resolution is a certain natural fragment of resolution which is in between tree-like resolution and unrestricted resolution. Yeah. So in this kind of resolution, you can think of it as a read once branching program, or you can think of proofs where every path from your axiom to the empty clause resolves every variable at most once. Yes, this is called regular resolution. Of course, this happens in tree, but it also happens in regular resolution. Regular resolution is a DAG that has this additional restriction placed. Okay, so in particular, the depth of a regular resolution is still going to be at most n, where if n is the number of variables. Okay, so all right, so historically, interestingly, the first proofs on lower bounds for resolution were proof for regular resolution by Tseitin in '66. This is the famous paper where Tseitin invented those Tseitin formulas. Yeah. And then it had to wait about 20 years before Armin Haken in '85 proved exponential lower bounds on resolution. Okay. And actually, strict separation from this came much later. Stallmark in '96 showed that tree-like resolution and regular resolution are strictly separated. And much later in 2007, Aleknovich, Johansson, Pitasi, and Urquhart showed that the same between resolution and regular resolution. So now, therefore, it makes sense to look at, because we cannot prove lower bounds and unrestricted resolution with parities, how about regular resolution of parities? Well, in 2022, Gryaznov, Pudlak, and Taliban-Fard, they introduced a certain model of regular resolution. Yeah, this was a very interesting piece of paper that introduced regular resolution with parities, and it followed from the lifting theorems that you could lift basically Stallmark's separation and immediately get a separation between tree-like resolution with parities and regular resolution with parities. Yeah, but we didn't know at the time when Gryaznov, Pudlak, and Taliban-Fard introduced their model of regular resolution, they couldn't prove any strong lower bounds on regular resolution with parity. So this even remained challenging. Before this breakthrough work of Efremenko, Garlick, and Itsykson in 2024, where they showed exponential size lower bounds for bottom regular ResLin. So I won't have the time to define these things, and we don't need it. It's a certain kind of, suffice it to say that, when you look at regular resolution with parities, there are like various different ways to do that. And this work did a certain way, looked at a certain kind of regular resolution with parities, which I'm calling bottom regular. And this was the binary or bit pigeonhole principle. And what an interesting thing that came out of this work is a very interesting machinery called the machinery of linear closures, which we will have a lot to deal with a little later, on a linear system on lifted variables. So this was the main takeaway from this work. This work invented a very nice linear algebraic machinery to deal with systems of linear equations, especially on lifted variables. We will talk about this more. And riding on this work, we were able to show soon. So this paper appeared in Stock 2024. Our paper appeared in Complexity 2024. That we could now then strengthen their lower bound, and also achieve a separation from regular resolution with parities and resolution with parities. Okay, and our work sort of combined many things. It combined this theory of closures that we borrowed from the EGI work, and we used this Aleknovich trick plus the stifling gadgets from the earlier lifting theorem. Okay, so all these three things combined to give us this separation. So that was the situation. And then in the last year, there has been very set of interesting developments, two interesting works that appeared that I'm going to talk about next. Okay. This next work was by Alexievich and Itsykson, which appeared in Stock 2025, so this year, where they proved, things for proofs of depth much more than n. So let me read this. If pi is a resolution with parity refutation of a Tseitin formula on an expanding graph lifted with a 5-bit majority gadget, yeah. Okay, and this graph is a log n degree expander, and the depth of the proof is asymptotically smaller than, so n log n, remember, is the number of variables times log of n. Yeah, so n log n is the number of variables because we're dealing with graphs whose degree is log n. Yeah. Then the size of the proof is 2 to the omega n. Okay, so they proved exponential lower bounds if your proofs are sufficiently shallow, but the upper bound on the depth that they needed was already way beyond n. So this proves, in particular, lower bounds for all kinds of regular resolution with parities, because the proof depth is strictly superlinear. Yeah, so that was a very important development. Okay, and this is just to be sure, do some accounting about the number of variables here. As I said, was n log n. So n is the number of vertices in the graph. Capital N is going to be the total number of variables in my formula. The number of clauses is going to be always polynomial because the degree of the graph is just log of n. And what they're saying is, therefore, is the proof size, the proof depth in the number of variables is much smaller than capital N times log of n, then the size must be exponential. So it's like a depth size trade-off. Okay. But the trade-off only works if the depth is at most n times log of n. Okay. And again, this paper it built on the machinery of EGI, very importantly, the earlier work that I just referred to, using the theory of closures in a very crucial way. But it also introduced a very interesting technique, a new technique of bottleneck counting that they call the random walk with restart. Okay. And this is going to be very important because we are going to build further on this technique. Okay. So currently, this is the best known technique that we know, which I'll explain, to deal with resolution proofs, with parity proofs of superlinear depth. Okay. So then in 2025 complexity, Efremenko and Itsykson, they were able to improve the lower bound of the earlier work of Alexev and Itsykson by same thing, except now the depth of the the depth of the proof is improved from n log n. Here you have n log n to n log of n. Yeah, so there was some improvement. But more than this quantitative improvement, this work, what it introduced is a refinement of, again, at this point, these things will sound not clear to you, but we will deal with it later. They invented another very interesting notion called amortized closure. Okay, the closure was what was EGI's contribution. This work, to me, more significantly introduces amortized closure, although the improvement in the depth was not that impressive. This amortized closure was a very nice invention. Okay, this is the new notion that this paper introduced, by which they were able to handle depth up to n log n. Okay, all right. And naturally, this latter work wondered if this theory of amortized closure could be used further to increase the depth that one can handle. So currently, until this work, the best depth that could be handled was slightly superlinear. Remember, capital N is the number of variables of the formula that you're trying to refute, and you're just being a little bit above n. Yeah. So the main question here was then, can I show n to the 1 plus epsilon, right? Strictly superlinear. Yeah. So that was the main question that they posed. And our main result is that we can indeed do so. So the main result that we're going to talk about is that if you give me a parity refutation of a Tseitin formula lifted with a very different gadget, yeah, they were using a majority of 5, technically a 2-stifling gadget, but we are not using stifling. We're using something some very different analytic property, which I'm going to talk about soon. Let's say I have now inner product on order log n bits. Yeah. So if you lift a Tseitin formula on an expander graph, this could be a constant degree expander. So G is now a constant degree expander, and you lift it with inner product. Yeah. Number of vertices is n of this graph. So the total number of variables that appear in this formula phi of G is order n. And the depth of pi, the depth of your proof, is just a little shy of quadratic, n to the 2 minus epsilon for any constant epsilon greater than 0. Then the size of the proof has to be exponential in n. Well, in particular, 2 to the omega n to the epsilon. So like if epsilon is 1 over 100, then this would be 2 to the omega n to the 1 over 100. You can make epsilon arbitrarily small, but a constant. Okay, so that's the main result. Okay, and this is again my accounting about the number of variables. So the total number of variables here would be n log n because the inner product gadget is on log n bits. The expander graph is a constant degree expander. Yeah, and so I have just rewritten everything in terms of the number of variables of the formula. And the interesting thing, as I was saying, that the inner product gadget is just one of many gadgets that one could use. The key gadget property the stifling gadget the property of stifling for a gadget was what I would call a combinatorial property, and we are using an analytic property. So if G is in particular, if G is a gadget, which is a function from b bits to 0, 1, what I want is every Fourier coefficient of G to be exponentially small in b, right? The Fourier coefficient is just, the Sz Fourier coefficient of G is the correlation of G with the Sz parity. Okay, so the property that we demand for this thing to work is that every Fourier coefficient of G be this small. Yeah, so if it is 2 to the minus alpha b, then the gadget size is 2, like 1 over alpha times log n. So it's inversely proportional to alpha, and for inner product, alpha is well known to be half. Okay, so for any constant alpha, this would work. So I'll take a pause, and this is the statement of the main result. So, you should, if you have any questions, please let me know. So I'm assuming there are none. So let me continue. Okay, so
you are going to say more about the thinking about the stated property of the gadget was a bit fast, but you're going to say more about this later, or the significance of the.
I'm going to say more about this later. All I'm saying currently is that I hope the statement of the property was clear. Was that not clear, Jakob? Do you want to hear it once more?
So no. It's but the statement is clear. The why it should be relevant is not so clear.
Well, it
and also, could you say what this alpha thingy is again?
So alpha is a constant. What I'm trying to say is, there exists an alpha. So the quantifier over alpha is there exists an alpha such that all Fourier coefficients. So I'm trying to choose a gadget C which satisfies the following property, that there exists a constant alpha such that every Fourier coefficient of G is the magnitude is at most 2 to the minus alpha b. B is the number of bits on which the gadget G depends. So it's exponentially small. The exact way the exponent appears is with this alpha. So there exists some constant alpha. The quantifier is existential. Yeah. And let me just comment on this one thing that you said is, why should we expect this property to come in? In some sense, it's very natural, right? Because the gadget G is basically itself very hard for parities, right? This is exactly what this analytical property is telling you, right? It correlates very poorly with every possible parity. And we're dealing with resolution with parities.
And then the final line is just saying that you expect this gadget to have growing size, but it's going to be like logarithmic. The arity is logarithmic in n with some constant.
Exactly.
Okay.
Currently, we are not able to bring down the gadget size to smaller than log of n. But, so it's interesting because, log of n, so our graph is now a constant degree expander, but atop that graph now we have a log n sized gadget. Okay. But log n is not a problem, as you said, because, if you're lifting with a log n sized gadget, you still get polynomially many clauses. Yeah, it would be much better, of course, if you can do it with a constant size gadget. That's an important challenge, I think. Okay. All right. Okay, so let me move on. Yeah. So now I'm going to try to explain what were the problems and why this previous works were stuck at n log n. Where does this number n log n appear? What do we do to go beyond n log n and go to n squared? Yeah. So to do that, I'll have to tell you the basic random walk plus a restart technique of bottleneck counting that was introduced in the earlier work. And let's do that. And I would like to tell you the first part of this that I'm going to tell you is not going to at all talk about resolution with parities. We're going to only deal with just resolution. And I want to convince you that even just dealing with resolution, this random walk plus restart is a new way of proving lower bounds for resolution itself with its limitations. And a very natural approach of doing random walk with restart on even a resolution DAG hits the barrier of n log n. So it wasn't a surprise that the earlier paper got stuck exactly at n log n. Okay, let me explain that. Okay, so let's first look at random walk. This idea of random walk was done in the first work of EGI. Okay, so I'm going to illustrate, as I said, with just plain resolution. So here's a resolution DAG. There's no parities here. And in a resolution DAG, you query these things. You make ordinary queries, like you're querying. You can view this as if you traverse in this way, you're making queries with just ordinary, like Z1. So you're querying here Z1. If it's 0, you go left. If it's 1, you go right. Right. And at any point, if the size of my DAG is S, at any point, if I'm at a certain distance Q, the total number of nodes that I encounter is S. So either S is very large, so it's already like a tree, or S is small, polynomial, then you didn't allow your graph to grow like a tree, so you must have forgotten a lot, right? That's the idea. And this G is going to refer to the expander graph on log n degrees that the earlier papers used for our Tseitin formula. Okay, so we're trying to understand why, if I look at a resolution DAG for a Tseitin formula that arose from such a graph, such an expander graph, the resolution DAG finds it hard. Okay, so look at a path from the root to a particular vertex. Yeah, and let's say this path is somewhat it's like n over 1,000 distance. Yeah. Now, what happens when you make Q queries to this? You're traversing this path because you've chosen a certain assignment to your variables in the formula. And as you make queries, you had one expander graph. So when we look at expander graph, normally it's a connected component. There's just one it's a connected graph. And as you query this graph, the expander graph on which you're working starts fragmenting into components. But because it has good expansion, yeah, by just using the expander mixing lemma or Cheeger's inequality, whatever you call, you can always show that there's going to be one huge connected component, right? That's going to be of size n over 2, yeah? And at this point, sorry, don't ignore this only odd component. You don't know whether it's the only odd component, but you know that there's a big component, a giant component, which is there because you have made only few queries, as few as n over 1,000, and therefore, you've not been able to fragment the large component into smaller pieces. Okay, there's one large connected component surviving. And now the main thing to see, which is what the earlier work showed, is that if you took a uniformly random Z, yeah, then, well, I mean, no matter what Z you took and you made few queries, you have one large connected component. But then if you took a random Z, then with sufficient probability, small but appreciable, you will have the property that, your Z is going to violate a clause which is arising from a vertex in this giant component, the largest component. I'm calling C1 to be the largest connected component. Yeah. Remember, I built a Tseitin formula. Associated with every vertex is a clause, and every Z must have violated some clause. Now, the main thing to understand is if I choose a uniformly random Z, then with tiny probability, but still non-trivial, there's this chance that, somewhere here, there is a vertex, which is where Z is falsifying a clause. Okay, this is the important thing. Okay, all right. Now, armed with this, I'm going to, get into this. Bear with me. This interesting thing. I'll call a partial assignment useful. Yeah, because remember that a partial assignment is always going to split my graph, right? the original one connected component into various components. So I'm going to look at a partial assignment to the edge variables of my graph. It's useful if this row happens to split it up into these connected components, and the largest connected component has sufficiently large size, n over 2. Yeah, so then this is useful because, you know, the largest connected component is still not become too small, but this will be always satisfied if the number of assignments 0, 1 is small. But the most important thing is that, well, only this connected component is odd. Yeah, that means, you know, this is if you look at the charging functions, the charging function is odd only in this connected component. In every other component, it's even, so they can be satisfied. So the unique clause that has been falsified lies somewhere in the vertex, in some vertex associated with C1. If that happens, then I call my partial assignment useful. Yeah, in the sense that this partial assignment is maintaining the hardness of my formula. Yeah, that's why I call it useful. And you know, in a DAG, in a proof DAG, whenever I'm at a particular vertex, there's an associated cube, right? This is an ordinary resolution DAG. And a cube has fixed some of these vertices, some of the variables. So a cube is naturally associated with a partial assignment. If that partial assignment is useful, I'll say the cube itself is useful. Okay. All right. Now, the main theorem of Alexeyev and Itsykson was to say, and that, you know, for every useful cube, no matter what useful cube you have, as long as it's useful and its codimension is not too large. Yeah, this is the number of variables. So it's smaller than, you know, some small constant times the total number of variables. No matter what decision tree you choose, every decision tree of depth slightly smaller than the full possible depth. Yeah, the probability that, you know, when you choose Z at random from this cube, yeah, you're choosing a Z at random from this cube, and you look at Z, the partial assignment induced by Z in the following way. Well, Z was run on this decision tree, so some of the variables T had queried, so those variables got fixed by the path that Z traced out. Yeah, so we look at those variables. And well, you started from a cube A. So the A also had fixed some of the variables. So you look at this combination of fixing. The T fixed some variables and A fixed some variables. And you look at Z, the partial assignment that you get by looking at the projection of Z onto those fixed variables. The probability that this partial assignment is useful, yeah, because that's what the cube remembers. So if what it remembers is useful, is, as I said, tiny but sufficiently large, 2 to the minus order n. Okay. So this is the main observation of Alexeyev and Itsykson. Yeah. And now, armed with this observation, they come up with this ingenious step, which is the following. Well, now, you know, suppose I start from my root, yeah, and notice that as in the DAG, when I trace out a path, you know, it's like I have a decision tree and I'm querying various parts of Z. Yeah. So because, you know, there is only S many things over here. Okay. So as I said, if I choose Z at random, I'm going to end up somewhere where, you know, if I look at this cube is going to be useful with sufficiently good probability P. Moreover, I have only S many nodes over here. So there is a P by S fraction of nodes which I am going to reach. Yeah. So sorry, there exists a particular node. Let me back up. There exists a particular node V such that, you know, P over S fraction, because there are only S many things, P over S fraction of these Zs, yeah, which have this property that on reaching the cube that they reach is useful. Yeah. So P by S fraction of such Zs must land up at a particular node V. Yeah. Such that, well, if that has to happen, then what do we know? Well, if P by S fraction has to reach there, then the codimension of this cube cannot be too large, right? Because if the codimension is too large, that's what the bottleneck is. It cannot account for too many assignments reaching it. So codimension of AV must be at most log of S over P. And because P was 2 to the minus On, and if S is also about 2 to the order n, all in all, when I take log, it's order n. Notice that the number of variables, total number of variables is n log n. So this is still a bit smaller than the full dimension. Yeah. So if I sort of fix, so I have such a node V, and if I arrive at this node, well, the DAG has forgotten everything except the variables that are fixed by this node. So if I fix those order of n coordinates, I'm still at a useful assignment. That's exactly what this argues. So I'm able to find a V which is small. That's what the bottleneck count, whose codimension is small. And the partial assignment is still useful. Okay. So everything else has been forgotten by the proof DAG. And this is very interesting because as they now realized, well, why do I stop there? Because, everything else has been forgotten. I can restart from this node again. Yeah. And I can repeat this process because, the codimension of this cube was only order of n. Yeah. Not too large. And I can repeat this thing again because, I will just repeat this argument and be able to again find out a node W after taking Q such steps, yeah, such that the codimension of this W will grow, but will grow by an additional order n. Just as it grew from here, the codimension here was 0, it grew to order n, now it will grow by another order n. And I can continue this for order log n times, yeah, because after I've grown for about, if I do this for log n times, then the dimension would become n log n, and now I will be in, alarm bells would start ringing because the total number of variables, my ambient space, is already n log n. So I can do this, I can repeat this, I can restart my random walk for log n times about, and still, be okay, right? So all in all, this just says that if my proof, if DAG had size 2 to the little o of n, its depth must be omega n log n, right? Because each time I'm walking, I'm doing n log n walk, and I can repeat this order n, so I will be able to find some node at a depth of n log n, right? So this n log n was the total number of variables times this extra log. I hope that was clear. Okay, so yeah, and you notice that, so already with this just shows a different way of proving a size depth trade-off for ordinary resolution. Okay, so this is what I've written. Just what I said, I've expressed it in terms of number of variables. Yeah, and the bulk of the work, this idea that I just explained on standard resolution, the bulk of Alexiev's, I think the conceptual idea was just what I just said. What Alexiev and Itsykson did was they used this linear algebraic machinery of the earlier work to lift this to ResLin. Yeah, you see here, n log n shows up very naturally over here, n log n. This is the, you can't, using this bottleneck counting, you can't go beyond that. Okay, so that's why this n log n shows up. And the technical machinery of Alexiev Itsykson just takes this idea, this conceptual idea of a restart, using the closure machinery, and they lift it to a ResLin DAG, which takes a lot of work. But in particular, they were only able to do that not all the way to n log n, but they suffered an additional loss of n log of n, and they could only show this for that. Okay. The next work of Efremenko, Itsykson 25, as I said, they beefed up this machinery of closure with amortized closure, and then they were able to match this n log n bound that we saw for resolution to ResLin. Yeah, they could now handle the same depth. Yeah, and as you can see, so that's the natural barrier now one hits post the Efremenko Itsykson work, because this bottleneck counting method, the natural way that they did is bound to get stuck at n log n because it gets stuck even for resolution in the way they did. Yeah, so of course it's going to get stuck with even resolution with parities. Okay, so I'll pause here because this is an important, I wanted to convey this idea that where does n log n, why does n log n show up? It shows up if you run this argument over resolution, ordinary resolution itself. Is this clear? If you have any question, please let me know. Okay, if you don't, let me go on. So, Jakob, there is, I would like to go on for another 10 minutes and then we can take a break. Is that okay?
That sounds good to me. You're in charge. 10 minutes more, roughly, and then have a break. That's
Yeah.
the plan.
Okay. Because I just want for the people who are interested in the first half to understand how to go beyond n log n. So what I would like to say is that uniform distribution, because we were choosing a random z, if you remember, we'll come to this argument again, is the root cause of the problem. Yeah, because that problem shows up in resolution itself, ordinary resolution DAC. Yeah, let's explain this. What do I mean by that? Okay, so notice the following. Suppose I give you an expander graph, yeah, of log n degree. It's a log n regular graph, and I give you a budget. So you have a budget of q queries to make on this Tseitin formula. So you're given an assignment to the Tseitin formula that has arisen from an expander graph, such an expander graph, and you can make queries to find out a falsified clause. Your budget is just q queries. Yeah. So a natural thing to try would be to isolate a particular vertex. Query all incident edges to vertex u1, right? So all the variables associated with this vertex, in the hope that, you know, the sum of this will turn out to be odd. Yeah. Actually, it should be and then you will have it falsified. Yeah. So and that would be your hope, but you know, suppose it actually this should be so the probability, if you choose a random z, the probability that this will happen is exactly half, right? Okay, so that you couldn't find a falsified clause associated with this u1, so you go to the next vertex and you keep doing this every time you're making log n queries, and you're hoping that, you know, one of these will succeed. So if you make q queries, right, then the probability that you, the prover, fail to find such a thing is going to be 1 over 2 to the number of vertices that you query, right? And because associated with each vertex you are making log n queries, so if your budget was q, this would be 1 over 2 to the q over log n. So this would be the probability that after making so many queries on a random assignment, you still did not find your falsified clause, and the falsified clause lies in some vertex associated with the largest connected component surviving. Okay, this is a very this would be the case for such a decision tree, and this is exactly where the you know, this 1 over 2 to the n was coming. And remember, q was n log n, so 2 to the q over log n was exactly 2 to the n. Yeah, so this is where you know, this n came in the theorem of Alexeyev and Itsykson, where they showed that for every decision tree you will survive, you will have the good situation, meaning where the prover will fail to find a falsified clause, and the falsified clause will lie in some vertex associated with the largest connected component with probability 2 to the minus order n. And we've just seen that you can't hope for getting a better probability bound, yeah, because a very simple decision tree gives you that, shows the tightness of that bound. Yeah. Okay. So the point is, at this point, we thought, like, why do we have to, you know, be stuck with the uniform distribution, right? Why do we choose uniformly an assignment z? We need not, right? Yeah. So what we observed was, now there's been a, sorry, this slide is a little, the quantifiers are written a little wrong. So read it this way, I'm reading it for you. For every useful cube A, there exists a distribution mu. Yeah. So sorry, for every useful cube A with codimension small, I meant to say this, for every useful cube A whose codimension is small, there exists a distribution mu such that for every decision tree, these are ordinary decision trees of depth smaller than the full depth, sufficiently small, gamma is a small constant. Now, if you sample z from the cube according to this distribution mu, not uniformly at random, yeah, and you look at the same thing that Alex and Itsykson were looking at, but now you look at z well projected down to all the variables that were fixed by the decision tree T and the cube that you started with. This partial assignment is useful, now shoots up to a very large constant, 1/3. Yeah, you can design a distribution mu, and in Sreejata's talk, he will explain you the distribution. In hindsight, it will look like a natural distribution, but there is such a distribution. It's very far from the uniform distribution. It's not at all the uniform distribution. It cannot be, right? We just argue. Okay, so there is such a distribution. So at this point, you might say, aha, now we are back in the game because we found this success probability, we have boosted it up. So now maybe we can do the bottleneck counting better, right? What was the bottleneck counting saying? Well, the bottleneck counting was saying that, well, okay, if you have that large a probability, if probability was P, then the codimension would only increase by log S over P. And because the P was very small, this was giving a large additive number. Now, because this P is large, well, it should be very good. But unfortunately, this distribution mu is not the uniform distribution. So you can't do this volume counting argument that I was doing before, right? You can't do that because this is no longer it's a weird distribution. Okay, so you can't use this, you can't do this simple-minded bottleneck counting idea. And the problem is because while you have boosted the probability, the distribution has turned out to be non-uniform. Yeah. So the first step is to find this distribution. Then the second step is how do you make this distribution somehow, still do the bottleneck counting? And the solution is, well, we're going to deal with this by going to, a lifting solution. Okay, we're going to lift with gadgets, and so much so that even to deal with ordinary resolution DAGs, we won't be able to do it without lifting. We don't know how to do that. Even to deal with resolution DAGs, even to do the same idea that Alex and Itsykson developed on ordinary resolution DAGs, coupled with this non-uniform distribution, we need a lifting gadget. Okay, and it turns out that we are lucky with a lot of technical work that argument is so powerful that it is able to deal with not just ordinary resolution DAG, but with resolution with parity DAG. Okay. I think this is a good stopping point because now I'll have to get into the linear algebraic machinery. Yeah, and so I think this is a good stopping point.
Okay. So as we are preparing to take a break, are there any questions at this point? One question is whether T and A are over disjoint sets of variables.
T
Question
and A.
being asked in the chat. I guess this is this good subcube and the decision tree, right? T and A.
Oh, no. This T and A need not be. The point is, you might assume they are because T, let's say T knows this A, so T could, there's no point in T asking the variables, querying the variables that have been fixed. You may assume because you are free. As I said, the quantifier is, I have this given your cube A, I give you the distribution mu such that it works for every decision tree. Yeah. So you could assume that you know A. So, you may not query them because those variables, have been fixed in Z according to A. Does that answer the question?
I think so. The way I understand it is like, I mean that you will I mean, the decision tree T, we can think of it as being hit by A, basically.
Yeah. Yeah. So this A is just, because Alexiv and Itsykson's random walk with restart, the restart here you have a DAG. If it was just a decision tree, then A would have been the full affine space. Yeah. Because you want to restart it every time, your affine space is going to shrink, or your affine cube is here, it was just a cube. The affine cube was shrinking in size, right? And you want to say that this argument continues to work even though the affine space has shrunk. So you want sort of a decision tree argument that works even though your space has been adversarially shrunk. You still have to make it work. It has not shrunk too much, because I assume that the codimension of A is still sufficiently small. Yeah, but it shrinks arbitrarily. Yeah, and this is like, it's like an extension of an argument that one would use for tree-like resolution, in the sense that you start from an arbitrary affine space, and you can keep doing this as long as the affine space dimension has not shrunk too much.
Any other questions from people who are posting in the chat, or maybe people wishing to unmute and speak? If there are no such questions, which currently appears to be the case, then I think we're preparing to take a break.
Okay.
So we are back after the break and continuing with Arkadev to hear more about the technical details. Please, Arkadev, the floor is yours.
Thank you. Thanks for sticking around. Just ask me more questions, because now we are getting into the technical parts. So the plan is, as I said, told Jakob, I'll just go for another between 10 to 15 minutes, and then Sreejata will talk about really technical stuff, very interesting stuff that I think is of independent interest beyond proof complexity, certainly. Okay, all right. So let me start. So as we saw, to have arguments that take us beyond n square, we needed to construct non-uniform distributions, right? Non-uniform hard distributions. And unfortunately, the bottleneck counting, the notion of codimension or dimension in linear algebra seems to be very attached to the idea of a uniform distribution, right? Rank seems to be a measure of how large you are or how small you are based on the uniform measure, right? So what do we do that, right? Even with cubes, we seem to have a problem. Well, the main idea is actually something that we had observed in our earlier work. Actually, my screen on the right is getting a little blocked. Is the same happening with you? Because of some panel that keeps showing up.
Everything is looking fine on my side, at least.
Okay, all right. So I'll continue. All right. So in this work in 2023 with Sreejata and Pavel Dvorak, we observed that lifting is a very nice way to fool the notion of dimension or rank. Yeah. When you lift it with a suitable, simple, constant-sized stifling gadgets, they will fool the notion. And let me just, so our current idea is sort of, making further, much more technical work beyond that. So let me just state the simple idea. There we had a very simple idea of fooling. Yeah. And so these would fool what we call any lifted distribution. So what do we mean by that? So suppose I give you an arbitrary distribution mu. Yeah. So now from here on, there will be two spaces. Yeah. We have an unlifted space, the space of the original formula, which having small n number of variables. And then we are going to lift that, which is what I call lifted space, where the total number of variables balloons up to n times b, where b is the size of the gadget. Okay, so given an arbitrary distribution mu on the unlifted space, here's a way to sample from the lifted space. And this is basically what I call sampling from the G lift of mu. So choose a Z in the unlifted space according to mu. And then you do the most obvious thing. Well, sample X in the lifted space by looking at every block of X. So remember, X has n blocks, each worth b bits. So for the ith block, this is where the ith block resides. Yeah, you're going to sample uniformly at random G inverse of Zi, right? So Zi is a 0, 1 bit because it's the ith bit of Z. And you look at the inverse image of G, inverse image of a 0 or a 1 at random. Yeah, the set of all points that map to 0, choose one at random, assign it to Xi. If Zi was 0, if it was 1, it's likewise. Yeah, and you do this for each of these blocks. Yeah, and that's your X. So that's a very natural way of choosing a lift of a distribution. This is what we'll call a lifted distribution. Yeah, given a gadget G and given a distribution mu, this defines a distribution on the lifted world. Okay, and what we observed. So this is what I'm going to call capital G inverse of mu. I'm sorry, this might somehow confuse you, but I was too committed down this line. So this G is not the Tseitin graph G, but this is the n-fold application of the gadget G, small g. Yeah. So this is what I'm calling the G inverse of mu. So mu is in the unlifted space. This gives you a lifted distribution. Okay. And what we observed was in that work was that we can fool things very nicely in the following way. Yeah, consider any affine space A. Now I'm talking about affine spaces. Yeah, in the lifted world, take any point Z over here in the unlifted world. Yeah. Now look at you're choosing X in the lifted world. If you were going to choose X uniformly random in the lifted world, then the probability that X would be in A by linear algebra, by just a volume argument, would be 2 to the minus the codimension of it, right? Okay, that's what a uniform distribution would do. But this lifted distribution, I mean, in particular, take a point Z, a fixed point Z, look at G inverse of Z, and you're choosing one at random from there. This would almost do the same in the sense that now the probability that X is in A is not going to be as nice as codimension of A, but by B, where B is the size of the gadget. Yeah, so if the gadget is a constant size gadget, for instance, then this is going to be pretty good. Yeah, so if G has to be a little bit more than a stiffling, it's something called balanced stiffling. It's a technical condition, but there are lots of such gadgets. Yeah, which will satisfy this. And this is a nice thing because now I can talk about in the unlifted world a convenient distribution that is convenient for me for one purpose, and then smooth it out sort of to full rank by using a gadget. This is the lifting solution. And that worked very nicely, wonderfully in that paper. This is how we were able to strengthen the lower bound of EGI, yeah, for a weaker formula. Okay. Now, unfortunately, this worked for regular ResLin there, but it doesn't quite work for ResLin or resolution DAGs when the depth is a little bit more than n. Yeah, because here we need to restart. Yeah, notice that this thing is talking about an affine space A. So you're choosing X uniformly at random from this thing, and you're looking at what's the probability it lands in A, right? Like this is good if you start from root and you're looking at any affine space associated with these nodes. Then the bottleneck counting would go through exactly for this reason, because I'm going to just find out what's the volume of this under this lifted distribution. That volume is small, right? This is what I'm saying. However, when I'm going to restart things, right, then I'm not going to be able to choose X completely at random. Yeah, I mean, because I have to choose X that lies in this affine space. Yeah, and because of that, this is not that old notion is not going to be enough. Okay, and here's an example that will convince us that that's not going to be enough. So, for example, consider this following X. Yeah, and G is some gadget. So the gadget G, I don't know what it is, but at this point, G is, so these are the various blocks, and in each block you have to apply G, and these red bits are the bits on which G is sensitive, meaning G, let's say output 0 on this particular block given this setting, but if you flip the red bit, G changes its value. So same thing holds for each of these blocks. Yeah. So we are considering such an X, and corresponding to this X, we have these two cubes even, right? This AW is the cube that fixes all these bits in exactly this way. Okay, in the way so that you get X. The only thing that resides in this cube is this assignment X, and AV is the larger space where all these sensitive bits are left free. So the unsensitive bits you have fixed, but the sensitive bits have been left free. So if there were n blocks, AV has n unfixed bits, right? So that's pretty large. Yeah. Now, as I said, imagine, so the codimension of AW, therefore, is at least n larger than the codimension of AV. So the codimension is substantially larger than the codimension of AV. However, if you consider the evaluation of the gadget G, so this is again n-fold application of the gadget G, this by design on this X is all 0, because as I said, small g was evaluating to 0 at each of these blocks. And if you now look at what happens, because I start from this AV, yeah, this is AV, imagine that was AV. So if I'm looking at X, I'm sampling from G inverse of 0, this is 0 to the n, this 0 is 0 to the n, at random, then the probability that X will lie in this much smaller affine space, conditioned on the fact that X did lie in AV, unfortunately is 1, right? Because, there's only one way if you think about it, because if these bits are not exactly set over here, this block is not going to output 0, and the same for each block. So the only way, if I know that X is a pre-image of G inverse of 0, and X was already lying in this AV, then X must lie in AW. Although the dimension of AW was, the codimension was n more. Yeah, so there is no exponential decay in n. The probability is 1. Yeah, and that's the difficulty. Yeah, if you want, so you need conditional rank fooling, right? Not only do you want to fool just X in AW event, but you want to fool the event that X is in AW, conditioned on the fact that you started from an X which lies in AV. And this simple idea, using a gadget, no gadget will be able to fool this. Yeah, I gave you an example, right? Okay, there are two things here. Yeah, if you notice, well, one irritating thing is that, well, this AW or AV was a very special kind of a situation, right? You fixed too many things inside each block, right? So somehow you have to, this happens often in communication complexity. When a block gets too much fixed, those are bad blocks, and you do something about it, right? You don't keep them flying around, so you need to do something about it, and only then can you hope for fooling things. Yeah, that's the message of this slide. Okay, so this is where I have to now get into how do we keep track of things becoming too crowded and blocks becoming too dangerous. Yeah, this is where the notion of a certain notion that was introduced in the work of Efremenko, Garlick, and Itsykson of what I would call spread affine spaces comes in, right? The theory of closures. Yeah, it will help us keep track of when things are becoming too crowded. Yeah, some blocks are becoming dangerous. Yeah, and what do we do about that? Yeah. So imagine I've been given an affine space, given by every affine space is given by a bunch of linear equations of this form. So this is like an codimension R affine space. There are R equations, and I have this is a particular representation. In a certain basis, there could be many different ways. I've just chosen one definition, one representation. And if you look at the span of this L1, sorry, there should be an R here, L1 to LR, this is basically in terms of linear algebra. Well, the affine space has a homogeneous component V whose translate is your given affine space, and it's the perp of that, the dual of that, right? That's the span of these linear forms gives you the dual of the homogeneous part of the affine space. If V was the homogeneous part, this is V perp, right? And here's the safety condition. We don't want crowding to be there. So there's a very natural way to state it, which is like a, in Hall-like condition. In combinatorics, this Hall's theorem in matching, it's exactly the same kind of thing appearing here. Well, we'll call a bunch of such, linear forms, L1 to LR, the affine, the perp space, the perpendicular space, the dual space, to be safe if the following things happen. If there is not too much crowding going on with respect to our blocks. Yeah. So there's like a linear algebra notion and there's a combinatorial notion of blocks, and we have to marry the two. Yeah. So look at any k linearly independent vectors in this affine space. Yeah, no matter what representation you started with, you look at the whole space, look at any k linearly independent vectors, they are well spread with respect to our blocks, in the sense that if you look at the support of each of these vectors, the support of a vector is the set of all blocks that its non-zero coordinates touch. That's the support. Yeah. So the support by definition is the set of blocks on which it is supported. So if you look at the union of those supports, it's at least k. If there are k linearly independent vectors, they must be touching at k or more different blocks. If this condition happens, this is like, if you look at a graph, you can think of it as a sort of a bipartite graph and exactly build like a Hall-like condition. And this is exactly like a Hall-like condition. The neighborhood should expand. So here I'm saying, the neighborhood should expand. The neighborhood of blocks should expand with this linear algebraic condition. Yeah. So this is a very Hall-like condition, and this is sort of saying that you should be well spread. Yeah. And whenever you have this, it takes a non-trivial argument. You can mimic the proof of Hall's theorem in linear algebra and get this dual view, which is very nice, which is a system of distinct representatives, or a matching, if you will, is that, this is true. This set of such things are well spread, safe in the left-hand way, if and only if there exists R blocks, yeah, without loss of generality. Let's say, well, I've chosen BI1 to BIR, and in each block I have some columns C1 to CR. So there are R blocks, and from each block I'm choosing a column such that those column vectors in this are linearly independent. Yeah, one side of this is easy, which is that if I give you, it's not hard to show that if I demonstrate you such a bunch of linearly independent columns, one from each block, and there are R blocks, yeah, involved, then basically you must be satisfying the Hall-like condition, you must be safe. This is not the difficult part. The slightly non-trivial part is showing the other direction, yeah, that this is an if and only if, and this, you can mimic the proof of Hall's theorem with a bit of linear algebra, and you will get that. Yeah, this was the very nice observation introduced in the work of EGI. Yeah, so the first part, okay. Now, so we call a space safe if the Hall-like condition is satisfied. Why do we call it safe? Well, first of all, just a remark that being safe is not a property of the particular representation, because we have been talking about fishing for vectors in the whole span. So it's a property of the affine space. It's an invariant of the affine space and not a particular matrix or constrained representation of it. Okay, that's a nice thing. And why do we say it's safe? Well, it's safe because of the following thing. If I give you an affine space which is safe, which is well spread, and G is any one stifling gadget. Yeah. Okay. One stifling is if I give you any bit, yeah, you can stifle it by setting the other bits in a way so that the value of G gets determined. So if I have an affine space which is safe and you have a one stifling gadget, then the following nice things happen, right? This affine space is very rich. If you give me any Z in 0, 1 to the n, this is in the unlifted world, yeah, it has got a representative in the affine space, meaning G inverse of Z. So look at the pre-images of Z in the lifted world, which will be mapped to Z by G. That pre-image set must have at least one representative in A. It's non-empty. Yeah. In other words, you can sort of think it as the entire cube, yeah, entire Boolean cube, the full Boolean cube in the unlifted world is present in A. It corresponds to A. Meaning if you've been given, if the adversary was so kind to have queried a bunch of linear forms whose span was safe, then effectively, correspondingly, in the unlifted world, the adversary has made no queries. Yeah, this is the correspondence. Yeah, so that is why this is what we would like to call a safe affine space. Okay, but things will not be always safe, right? As you progress in a DAG, often things would become crowded. The adversary would start, in particular, the adversary can start querying the bits of a block. And of course, then, all niceness breaks down. And that's what gets us into measuring the bad blocks. How do we measure, or how do we find out what are bad blocks? So this is what we call the d-violator of an affine system. Yeah. So a subset of blocks is a d-violator of my affine system if the following happens, right? This is like some set of bad blocks, in the sense that if I choose, look at any description of affine space in some basis, look at, just project this L1 to outside of S. Yeah, forget the S's. Yeah, look at what L1 is outside of S. Yeah, and LR is outside of S. Yeah, so the span of this is a restricted space. I mean, you just forgot about everything in S. So this lies in N minus S cross B, and this is a d-violator if that space is safe. Which means, if you think about it, which means when this happens, yeah, if you assign some assignment to these blocks, yeah, the rest of the system, if you make an assignment in the lifted space to variables of the d-violator, then you will get a reduced, you will get an affine space, induced affine space on this. That induced affine space is nice. So if you can somehow fix these blocks, you're good to go. That's the intuition. Okay. Technically, we define it in this way. And that's what I've just drawn here, right? So if you just, eclipse this, if you forget about these bad blocks, then this part is safe. Okay. And the closure of an affine space, which is one of the central notions here, the closure is a minimum d-violator. Yeah, you want to choose the minimum set of bad blocks, right? Which is making your system crowded in that sense, right? So that if you remove those set of bad blocks, everything is good, you become safe. So the minimal d-violator is called a closure. And the nice thing, and this is a lemma, it requires an argument, yeah, it's not obvious at all, is that the closure of A is a very nice measure. It's a very nice object. The closure of A is unique. Yeah, there are no two minimal d-violators. A minimal d-violator is a unique minimal d-violator. Yeah, and this is denoted by the closure of A. Yeah, this is how we are going to denote it. So this is one of the most. So the point is, if I assign, I can sort of think, I should defensively think that, as I'm going down my DAG, at some point the closure of A, the affine system that I'm in, is going to grow and shrink, grow and shrink. When it grows too much, the adversary, the proof or that affine space has fixed a whole bunch of variables. Yeah, this is the idea. And that's why it's important to track how the closure is progressing. So that's the, this is again, I just want to illustrate it by just a picture that, this is an assignment. Let's say Y is a closure assignment. By a closure assignment, I mean, here's V, and so there's a corresponding affine space. Just take any Y, which is an assignment which extends to the space, meaning there's a completion of Y to the remaining blocks and variables in the lifted space that is in AV. Yeah, so that's an extendable closure assignment. Okay, so I take any such extendable closure assignment, and if I now look at, if I use G on just Y, yeah, the closure assignment, yeah, so then I get something. Remember, closure is just a set of blocks. Huh? So then I get something in the unlifted world, a partial assignment only to those variables that in the unlifted world which correspond to the closure. Yeah, let's call that alpha. Now that alpha represents some cube in the unlifted world. Yeah, because like it's fixed. I've taken a closure assignment, so correspondingly in the unlifted world, those variables have been fixed, but as per alpha after mediating through the gadget, and this represents a cube. Yeah, which is where I said where variables here are fixed to alpha. Now the fact is, if G is a stifling gadget, then for every Z, yeah, which is in the cube, there is an correspondence with this measure, right? So I can think of, if I'm walking an affine DAG, I can keep track of this cube and assume that I'm making a corresponding walk in a resolution DAG. That's the idea. Yeah, where the resolution DAG's affine cube is sort of becoming like C alpha over here. Yeah, that's what we would like to believe, right? That's like a step towards lifting, mimicking what's going on in a resolution while you're walking on a ResLin DAG.
So the way I should think about this, if we're talking about in lifting terms, is the closure are the dangerous coordinates where the adversary has already gained enough information that I might need to commit. Exactly. But the safe space is sort of that's where I have nice density or min entropy or whatever my measure is, and where I'm going to be able to handle all coordinates, and I have full range lemmas and all these kind of nice things.
Exactly. Right. That's what you would like to. That's what exactly you would like to think of, and that's what would happen when we currently with a stifling gadget. This was not what I mean. Just to answer your question, or you continue thinking in this way, and at the end of this, I'll just tell you something, and I don't want to confuse. That's a good abstraction. Okay. All right. So now, unfortunately, it will turn out that, the closure is not going to be enough, right? Why? Because here's an dangerous or disadvantageous property of closure. Yeah. What is it? Suppose I have two affine spaces A and B, and the codimension, it's just, like B you made a query and B shrunk to A. The codimension of A rose by 1, the one query that you made, yeah, in the DAG or in the tree, whatever. But, you want this measure also sort of to reflect that, right? I mean, like you don't want this measure to suddenly, this set of bad coordinates in A should not suddenly become very large. But that can happen in a closure. Yeah. So that's the unfortunate property of this linear algebraic measure. While it is able to do a lot of stuff, there is this strange property that, there are affine spaces where even if you made one query, you did not anticipate this well enough, and suddenly the set of bad coordinates grew by a lot. And as you can see, that's not good. Yeah. Like in resolution, you would like to account it also by just one query. And in a resolution, when you are querying, the dimension of the cube does not grow suddenly. Yeah? So unfortunately here, if your closure does not honor that property, and this was the reason that the subsequent work of Efremenko and Itsykson addressed this by defining a new measure called amortized closure, which will be a sort of a smoothed version of closure, where this undesirable thing will not happen. Yeah. And you know, the technical way that they define it, and it's a bit technical. I won't want to tell you all about it. I don't have the time, but I just want to tell you that there is a way to define it, and defining it in the right way, amortized closure, disallows this stupid thing from happening. Yeah. So technically, what they do is they say lexicographically they want to choose the largest subset of blocks, so that for every j in S, yeah, there is some column. So there is one column from each of those blocks. These are indexes into blocks, yeah, so that the corresponding column vectors are linearly independent. So the important thing is, like, there's a natural ordering that you want to choose, so that this becomes a unique thing. This lexicographically largest thing makes this whole thing to be unique, and you want to choose the largest such thing. And it turns out that, you know, there are these nice properties. We wouldn't have the time to go through all of that. The two important properties, a few important properties that you should keep in mind is this measure is unique. Well, that's a giveaway because of lexicographically largest. But importantly, it's a measure that contains closure. Yeah. So, you know, if the closure hat, if the amortized closure is small, the closure, the set of bad variables is certainly small because it's contained in it. Yeah. So that's good. And again, if you are, you know, if you're increasing, if you're making queries, the closure hat grows sort of monotonically, right? So this is the monotonic property, because if A is a subset of B, so you got A by making one more query to B, or a few more queries to B, then the closure hat of A is a superset of the closure hat of B, because you might have made some more things bad. And here's the all-important property, which is what motivated the definition, is this thing. Like, if you got A out of B by just making one more query, one additional query, then the closure hat can increase at most by a 1. This is the all-important, very important property of amortized closure. This and the fact that it contains closure. So you get closure inside it, but you are able to, so sort of closure hat often will become, you know, it's a more defensive measure. Yeah, it's a more orthodox measure. It will grow even when closure is not growing, anticipating the fact that, you know, in future it might need to grow. Yeah, and it cannot grow by it should not grow by a sudden burst. Yeah. So therefore, you know, there could be an appreciable gap between the size of the closure and the closure hat, but the important property is it cannot grow suddenly in burst. Anyway, you have to play with this and think. The important thing to remember is that there is such a measure, and this measure, this notion is exactly technically defined in the way that I just said. Okay, and here's our main lemma, which is now the point is we're going to switch from codimension, which was such a uniform distribution biased measure. We're going to switch from there to amortized closure. Yeah, amortized closure is going to be the dimension of an affine space that we're going to track. Yeah, and in particular, what we're going to show is the following: that inner product fools amortized closure. What do I mean by that? So this is a particular property of any gadget that, of course, inner product satisfies. If you remember, when I stated my main result, Jakob asked about this. This is the property of a gadget G that just says that every Fourier coefficient or every correlation is small, right? So inner product in particular satisfies this. So if you take such a gadget, yeah, this is a much stronger property, then the following happens. Then the conditional fooling that we wanted, yeah, remember we wanted conditional fooling because we want to restart in the random walk. That conditional fooling is possible not with respect to codimension, but with respect to amortized closure. Yeah, this is our main technical lemma. Yeah. So what does it say? It says that suppose now I have two affine spaces. B is contained in A. Yeah, it's a smaller affine space. This are in the lifted world, such that the amortized closure of B has substantially grown from A. It's K more. Yeah. Now, if you choose any closure assignment, assign the bad things. So this is not closure hat, but closure. Remember, closure is contained in amortized closure. So these are the bad things that you assign in some way, because you need to assign. Yeah, take a closure assignment, yeah, which is extendable in A. That means, if you make this assignment, there are points in A which are consistent with that assignment. Yeah. Now take any Z in the unlifted world such that Z, the variables in Z exactly are the coordinates of Z that correspond to the closure of A are exactly fixed according to Y, in the sense that G of Y is that part of Z. Okay? Then the following happens. Yeah. Now if you sample X from this lifted distribution, G inverse of Z, yeah, such that and you sample it in such a way so that the fixed part is fixed. Yeah. So it intersected with Cy, so the cube in the lifted world where Y is fixed because you fixed it. So you're sampling G inverse of Z, you had to fix something. So that remains fixed. Otherwise, you're sampling from G inverse of Z. Yeah. Then, even condition that you lie on the big space because you did your restart from A, even condition that your X lies in A, the probability that X would lie in B is exponentially small in K. Yeah, that's what you wanted. If the codimension had increased by K, you wanted the probability to shrink exponentially in K. That happened in the uniform distribution. Here it's happening also exponentially, shrinking exponentially in K, even from a lifted distribution. Yeah, but we are no longer talking about codimension, but we're talking about amortized closure. Yeah. So if you replace codimension by amortized closure, then lifted distributions can conditionally fool amortized closure. And I would like to say that this is exactly what would give us the ability to restart and do bottleneck counting, even when we are working with non-uniform but lifted distributions. That's vital for increasing the probability of success. All right. Okay, so now I'd just like to wrap up. I have to go a few more minutes to say, remind you, why does this help? Let us just see. So recall what a useful partial assignment. So we were trying to see why, armed with this conditional and fooling lemma, we can go back to the random walk and restart and complete the argument for an n squared lower bound. Okay, so imagine, recall that a useful partial assignment is this assignment to the edges of my graph, so that the largest connected component is still pretty large. Well, and the only odd component is the large component. Everything else is even. And this was when we had said that A was a useful cube if the variables in the cube fixed. These are the things that the DAG knows is still useful for us. It doesn't know too much. It still doesn't know where the falsification happens. So, and this is what I alluded to, that if I go to a lifted distribution, then I can have this very nice property that if I start from any useful cube, yeah, whose codimension is not too large, then for every such cube, there is a distribution mu that's going to, be hard for every decision tree, even if it makes gamma n queries, just a little shy of the full number of queries, and I were to choose a Z uniformly, not uniformly, according to mu from A, then, the things that it had discovered out of Z, which is T union A, these are the coordinates that decision tree has discovered of Z from Z, it doesn't know anything about Z except these coordinates, that is still useful. Yeah, it cannot pinpoint the falsified clause. That happens with large probability, 1/3. Yeah, this was the power of choosing a non-uniform distribution, because this probability increased from 2 to the minus something large to all the way to 1/3. Yeah, but we had to introduce uniform distribution. And now we want to say, how can we do this? How can we use this non-uniform distribution to do our bottleneck counting? And for that, I have to give you one more idea, which is that I'm going to now talk about, I want to get into, jump into affine DAGs and not resolution DAGs. So now I have to talk about affine spaces being useful, right? When does an affine space become, so instead of a cube, now if I have an affine space, it's useful in the following way. I'm going to use closures, right? Every affine space, corresponds to one or more than one cubes in the unlifted world via this closure. Take an assignment to the closure variables of this affine space, yeah, and look at what G does to that assignment. Well, the gadget is going to turn that into a partial assignment in the unlifted world. And if you have an extendable assignment to the closure variables, which is turned into a useful assignment in the unlifted world, then I would say the affine space is useful. Yeah, so I can I have an affine space and I can map it to a cube in the unlifted world where the adversary knew very little because the affine cube was useful. Then I would call this affine space useful. Yeah, that's it's a very natural idea. And so this alpha is going to be G and Y. Yeah. So for every useful alpha, so this alpha represents a cube or a partial assignment, I will have a hard distribution. This is what we just showed here. Right? So I have a hard distribution corresponding to every partial assignment in the unlifted world. Yeah. And now we're going to deal with not decision trees, because I have to make my walk on a parity DAG or a linear DAG. So I'm going to deal with parity decision trees, right, rather than decision trees. So here's a parity decision tree where I'm going to query linear forms, right, linear queries instead of regular ordinary queries. Yeah. And here's one last piece of notion. So, if I take an X and feed it into a parity decision tree, it's going to induce a walk on this tree. Yeah. It's going to induce this blue colored walk. Sorry. Yeah. And as it walks along, it's querying some linear forms, and that's obviously going to give rise to an affine space, which I'm going to call the induced affine space, the affine space that X leads to. It reaches a leaf, and there is an affine space associated with that leaf of the tree, which I'm calling AT of X. Yeah. And okay, now armed with this, I'm going to state the last theorem that we need that will help us achieve our goal, is that now we're going to prove the analog of the cube lemma that we had, the success probability lemma that we had proven for ordinary decision trees. Yeah, this is a bit of technicality because we need to prove we saw that we could design a distribution mu that was giving us good probability of reaching a useful node if the decision tree or the DAG was an ordinary thing. We want the same now for affine, but using a lifted distribution. Yeah, and that's exactly what this lemma is saying, that if I start from a useful affine space whose closure, the size of closure, the set of bad variables is small, yeah, it's not too large, yeah, then for every parity decision tree of depth, q less than gamma n, I'll have the following thing. Yeah. So because, notice that this alpha, what is this alpha? This alpha is associated. So there is a closure assignment. There's a way to assign the variables which corresponds to alpha being assigned to the unlifted variables, right? Giving an assignment here to the blocks in the lifted world corresponds to some assignment in the unlifted world. Corresponding to that, there is a hard distribution mu in the unlifted world. Yeah, and now we are choosing this lifted distribution. Yeah, in the lift, yeah, G inverse of mu alpha. And of course, we have to lie in this affine space because that's the node that we have reached in the random walk. Yeah, so I'm choosing an X from this distribution intersected with this space that I have reached and I have to lie in, and the fact that I have assigned this closure as per Y. Yeah, I've assigned the closure variables to Y. So the probability when I do this, the probability that when I do this walk, yeah, so this, I have a decision tree. Yeah, so sorry, this let me just read this for you. This is exactly, you know, so this parity decision tree, given this X, made some linear queries, reached an affine space, yeah, on the leaf, and then you have to again intersect with A and CY because we may assume that these are already known to the decision tree. Yeah. So now if you look at, this is the new affine space that you have reached, so to say. And you want that, you know, X projected down, so you want to apply G. So this affine space has its own set of bad variables. Yeah. This is this new set of bad variables that you have reached. And you want this set of bad variables, when you look at apply G to it, you will get a bunch of a partial assignment in the unlifted world that has to remain useful. Yeah, because you want useful things to be happening. You want to make it correspond to some useful thing happening in the unlifted world. And this probability is at least 1/3. Yeah, so you have to prove this. And this proof is non-trivial. In particular, it will require this lemma, the conditional fooling lemma. So anyway, now I am all set to do the final random walk and restart for the lifted distribution. Any quick question before I do that? Here's the lemma. I mean, I'll just stare at it. I'll let you stare at it for a while. This is just the PDT analog of what was happening in the decision tree. The decision tree I could deal with decision tree if I was only dealing with resolution DAG. Because I have to deal, I want now to not only deal with resolution, but ResLin, I have to deal with parity decision tree, and this makes things more difficult. And this is the analog of the earlier lemma for parity decision tree. Okay, so now how do we complete this? So here we are. I have started from the root, yeah, and I'm taking an excursion which is like, you know, gamma n long. I'm taking a walk and I'm going to reach somewhere, I don't know. Yeah, okay, and so sorry, I'm going to assume that, in fact, let me start from here. So let me not start from the root, because from the root we saw that it was easy. Things became more difficult when I start from an intermediate. How do I restart? So suppose I have reached, somehow magically I have reached a good node V. Yeah? Good node meaning if I look at the affine space associated with it, yeah, then the closure hat, yeah, the closure, not just the closure, but even the closure hat is formed. Yeah. You know, now suppose I do an assignment to the closure of this affine space AV. Let's call it Y. So I'm assigning the closure, the bad ones, the bad blocks. I'm giving it some assignment, and G takes it to alpha in the unlifted world, and alpha is useful. Yeah, this is what I'm assuming. This is the invariant I'm assuming that I'll always be able to reach. Now, what I want to show you is that assuming this invariant, that I'm in a good node, how can I continue my work? Can I continue? Yeah, that's the thing that we need. Yeah, and so let's say good is a set of all, starting from here, the set of all x's that lie in AV. Yeah, and when I walk, sorry, if I look at, you know, the closure hat of AV, sorry, the closure of AVX. So I'm taking a walk from here. Yeah. So this thing, if you can recall from here, this is the notation. Yeah. So I have some decision tree. The decision tree is represented by this part of the DAG. I'm going to take a walk. Yeah. And I'm going to reach somewhere. Yeah. When given X, I'm going to reach somewhere that's going to define an affine space. Yeah. So I'm taking the closure of that affine space. Yeah. And I'm looking at X, the projection of X onto those blocks, bad blocks, applying G, and it's still useful in the unlifted world. These are my good X's. Yeah, those are my good X's. I want to stay with those X's. Yeah. Not all X's may be good, but let's say I look at those X's. Yeah? So now the point is, just by the previous lemma, we know because this the size of the closure here was small. Yeah, if I sample X according to this lifted distribution, yeah, condition that on the fact that it lies in AV and it fixes according to Y, the probability of X being good is pretty large, 1/3. That's what we just proved earlier. Yeah, so the number of the X's that are good is pretty large. Yeah? It's the probability is large. Yeah, probability weighted according to this lifted distribution. Okay, and now, well, there are at most S many nodes over here. Because there are at most S many nodes, again, by a union bound, I can find, or pigeonhole if you say, there is some node W, yeah, such that if I choose one of these good X's, if I choose an X, then the probability that it will be good and it will end on this guy, this fixed guy, has to be 1/3 divided by S, right? Because there are S many nodes. Yeah, this is just by pigeonhole principle. One of them has to account for a good fraction. Yeah, so that's how I locate this guy. Yeah, okay. Now, well, the point is, now if I apply the fooling lemma, the conditional fooling lemma, this is going to say, this is exactly what the conditional fooling lemma is going to say, right? Because, you know, the probability, if I'm choosing from, you know, this is the same as conditioning on X lying in AV. Yeah, so this is the same saying X is being sampled according to G inverse of mu alpha intersected with Cy, conditioned on X lying in AV. Yeah, so, you know, the probability that X will lie in AW, if the closure hat of AW grew by much more than 2 log S, the conditional fooling lemma would kick in and say the probability cannot be as large. Yeah, this is exactly where closure hat comes in. This is what we used to do earlier by the dimension argument. We cannot do that anymore. Yeah, so first by using this, we look, the probability has shot up. So the probability of reaching, you know, reaching a node, reaching a useful X has shot up to 1/3. Then I use this argument to locate a W where it's 1/3S. So this probability is now substantially larger. And now I want to say that if the closure hat of AW grew too much over the closure hat of AV, yeah, more than 2 log S, then I can't have this probability. Yeah, this is what the conditional fooling lemma just did. Yeah, and therefore I am forced to conclude that, well, you know, if I take this walk, because this is S is small, this thing must have forgotten a lot of things, and therefore the size of the closure hat remains under control. It only grows by 2 log S over what it was already in V. Yeah, this is what the conditional fooling lemma does. Yeah, so now if you just plug in the size bound of 2 to the n to the epsilon and plug it into this, then we just find out that you know, it's growing every time by 2 log S. So log S would become n to the epsilon. So this is growing by n to the epsilon. So we can repeat this n to the 1 minus epsilon times before it breaches the n mark. So we can repeat this n to the 1 minus epsilon times. And each time we are making a walk of length n. So there must be a w, which is at depth n to the 2 minus epsilon if the size is much smaller than 2 to the n. And that is how we are going to complete the restart, the random walk with restart. So we are always going to be able to find a node w whose closure hat size has not grown. Because the closure hat size has not grown, closure hat contains closure, the set of bad variables also has not grown by too much. And we can play this argument for enough number of times, in particular n to the 1 minus epsilon times, way more than log n times, which is what was happening in the work of Efremenko and Itsykson. And therefore now we can reach n to the 2 minus epsilon. Okay, I probably lost many of you, but that's it. I'll stop there. Yeah.
May I ask
Thanks
a
a lot,
question?
Arkadev. There's a question already. Yes, Dmitry?
My question, where do you use that the size of a gadget is logarithmic? Only in conditional Fooling lemma or?
Only in the conditional Fooling lemma.
Okay, thank you.
You're absolutely right. In the conditional Fooling lemma, we need a union bound. And if you're, as you are obviously, very well versed with the lifting theorems, the lifting theorems also have a log n size, because in one way or the other, you apply a union bound somewhere and that union bound is expensive, and therefore, you grow your gadgets up to log n.
Thank you.
Okay, I'm sorry I took a lot of your time. But yeah, I mean, I'm sure Sreejata is dying to go ahead and show you the conditional proving lemma. I think if you sort of at least let him tell you about the conditional Fooling lemma, because the conditional Fooling lemma, I think, is independently interesting, and it should find use beyond proof complexity. Or yeah, in some sense that was the key. So should we have Sreejata now?
Yes.
Thank you.
Yeah, thanks. So, how much time do I have approximately?
That's a very good question. And I don't know if I have a good answer. I mean, we have been going for over 2 hours already, which is usually we don't do that. But I mean, since we're all here and people are free to leave whenever they want, but I think we probably want to keep it focused, let's put it that way.
Sure. Okay, Arkadev, can you stop sharing your screen?
Yeah, I'm trying to. So, how do I stop here? Something. Sorry. So,
Are you managing to unshare? Otherwise, I'll probably just, let's see. I could maybe just overtake. Let's see.
can you force me to unshare?
Yeah, I think I'm going to force you to unshare.
Okay.
Maybe
Thanks.
can I do that? Now it should be free to share, I think.
Yeah. So, is this visible?
Yes, but it's not. Yeah, it's not
Yeah,
full
yeah,
screen.
yeah.
Yeah.
I'm going to full screen just.
Okay.
Yeah, is this fine now?
This looks utterly amazing.
Good. So, okay, I'll just do the proof of the conditional Fooling lemma. And the rest of the proof was supposed to have two parts. The second part I'm going to skip unless people ask me to go over that. So here is the Fooling lemma that Arkadev was mentioning. Here we have two affine spaces, B and A. And the amortized closure of B is K mod and the amortized closure of A. And we are given an A extendable closure assignment to the variables of closure of A. And we are given any distribution on the unlifted world such that every point in the support of mu is consistent with the partial assignment that that y gives. Now we sample a sample a x according to the following manner. First, you sample according to mu, then you sample a uniformly random pre-image of that point, and then you condition it on being consistent with cy. So cy is the set of all points that are consistent with y. And we want to say that as we sample x according to this distribution, conditioned on x lying in A, the probability that x lies in B is at most 3 by 4 power k. So I'm just going to restate this here. So we have two affine spaces. The smaller affine space has the amortized closure of the smaller affine space increases by k. Yeah, this is the same thing. Yeah, so mu is a lifted distribution such that every point in mu is consistent with y. Now we sample z from mu and sample x to be a uniformly random pre-image of z. And we want to show that conditioned on x being in A and x being consistent with y, probability x lies in B is at most 3 by 4 power k. And the crux of the proof is the following equidistribution lemma. Recall that a safe affine space is an affine space whose closure is empty. And recall that Arkadev mentioned the property about safe affine spaces. If you have a safe affine space and the gadget is one stiffling, for any point in the unlifted world, there is a preimage of that point inside this affine space. Now here we are claiming something much stronger. If the gadget has all Fourier coefficients small enough, consider the following distribution. You sample a point uniformly from this affine space and output the gadget to all its blocks. Then you get a point in the unlifted space. We claim that this distribution is very close to uniform. In particular, for any z, the probability that you evaluate to z is 1 plus minus 1 by n power 50 times 1 by 2 power n. In case of a uniform distribution on the entire space, you would expect 1 by 2 power n. And we are claiming it's very close to that as long as this affine space is safe. And note that this also formalizes the intuition that in a safe affine space, you have essentially made no queries because your equations do not concentrate on any small set of blocks. And this equidistribution lemma is going to give us our conditional fooling lemma. We'll see that. So we start by proving this equidistribution lemma. Now recall what A being safe means. Let M be the codimension of A and let capital M be a matrix for the defining equations of A. Now A being safe means there exists small m many blocks and one column from each block such that those columns are linearly independent. So let's write this set of equations in a more convenient form first. Since this set of columns are linearly independent, we can perform row operations on this matrix so that reduced to this submatrix, we get the identity matrix. And note that row operations do not change the underlying affine space, so we are allowed to do this. So after doing some row operations, we get that this restricted submatrix looks like the identity matrix, where each column comes from a different block. So now let's rearrange the blocks so that the first m blocks form the identity matrix. So from the jth block, you have chosen a column Cj, and restricted to these columns, this matrix looks like the identity matrix. Now here is the crucial observation that we are going to use. Suppose you sum up any subset of these rows. Note that each row is a linear form. So you sum up any subset of the rows. Now take any j in T. Suppose you sum up a subset capital T of the rows. Now look at any j in T. So this sum LT will have a non-zero coordinate at the jth block because this jth column contributes 1 to the sum and none of the other columns contributes anything to the sum. So for every subset, every block in that subset will have a 1. We're going to use this property pretty soon. So recall what we wanted to show. Probability that as x is uniformly sampled from A, the gadget applied to x equal to z is close to 1 by 2 power n. And this is equivalent to showing probability that as you sample x uniformly at random from the entire space, x lies in A and the gadget applied to x evaluates to Z is close to 1 by 2 power n plus small m. Because to get this, you can just divide by 1 by 2 power n. So we are going to show this equality, this rough equality. So to do this, we perform an exponential sum calculation. So we start by writing down an analytic expression for x in A and the gadget applies to x equals to Z. So here is an expression for x is in A. X is in A if and only if all the linear forms are satisfied. So this is and over all j in small m, inner product of Lj comma x equals to Bj. And note that this value is an F2 value. So we can write this in the following. We can arithmetize this expression as product of 1 plus minus 1 power Bj plus inner product of Lj comma x. And we do the same thing for the other expression. Indicator of the gadget applied to x equals to z is the and over all coordinates. Indicator of the gadget applied to the kth block equals to the kth bit of z. And again, this is something, this is an F2 term. So we can again arithmetize this as half into 1 plus minus 1 power g of kth block of x plus zk. So we multiply these two together. We want to estimate the following quantity. Expectation as you sample x uniformly at random, indicator of x lies in A and indicator of the gadget applied to x equal to z. And we write down whatever expression we get. And we want
This
to
is
analyze
going
this.
to be extremely small because G is really not correlated with any of these linear guys. If we just, is
Yeah,
that
so
sort
it's
of
going,
what's going to happen?
yeah. So it's going to be extremely small, but we want really precise estimate because we want to show this is close to 1 by 2 power n plus m, which is also a very small quantity. So we want to show it's very close to this small quantity, and the error terms are even smaller compared to this already small quantity. Yeah, right. So where does the term 1 by 2 power n plus small m come from? It comes from the term where you pick this one from each of the brackets. So there are m small m brackets here and sorry, is my mouse pointer visible?
Yes.
Yeah, okay, good. So where does the 1 by 2 power n plus small m come from? It comes from the term where you take one from each of the brackets. So there are n plus small m brackets. The denominator is 2 by n plus small m. And if you collect one from each of them, you get this term, which is what we need. And now we want to bound the total magnitude of the other terms, which will be the error terms. And this will be small because, like you said, the FN space is safe. So, and the gadget has all small Fourier coefficients. So it has small correlations with all parities. So let's write down what we get. P is the expected value, the probability that we wanted to compute. Now, the central term is the term where you pick one from each of the brackets. So that is 1 by 2 power n plus m. So P minus 1 by 2 power n plus m is the summation of all these error terms. And we want to show that their total magnitude is bounded. And let's notice what those error terms look like. So each error term is indexed by two things, a subset S of 1 to m and a subset T of 1 to n. These denote from which set so capital S denotes the terms from which you pick the second term in the first grouping, and capital T denotes the terms from which the brackets from which you pick the second term in this second expression. So here we are summing over all subsets of small m and all subsets of small n such that their union is not empty, because the term where their union is empty is the central term. And we get some error term which we want to upper bound. And what we will do in the proof is we will analyze what these error terms look like. But first note that there are 2 power n plus 1, 2 power n plus m minus 1 many terms in this summation, which looks bad. And however, the claim is that most of these terms actually vanish. And this is why we'll use the fact that the FN space is spread. So here is the claim. If S is not a subset of T, the error term corresponding to S and T will actually completely vanish. And to see this, we just have to write down what the error term looks like. So define the following function of X. So recall what S and T were. S was a subset of the linear forms and T was a subset of the coordinates. And the error term you get if you expand that expression out is the following. Define G of S comma T of X to be summation of J in S, Lj of X, where Lj was the jth linear form, plus summation K in T, the gadget applied to the kth block of X. So this is some function of X. And the expectation of, and the error term corresponding to S comma T is the expectation of -1 power G of S comma T X. And we are claiming this vanishes. That means G of S comma T X is 0 for exactly half of the values of X and 1 for the other half. And this is where we are going to use the observation that for any J in S, the linear form summation Lj has a coordinate in the jth block, has a non-zero coordinate in the jth block. So so here's the claim. If S is not a subset of T, this term vanishes. So if S is not a subset of T, there is some C that is in S but not in T. And from our previous observation, which we got from the fact that the affine space is safe, the sum Lj for J in S has a non-zero coordinate at some column in block C. And suppose this column is C comma M. Now note that this column was not in T because C is in S minus T. So if you flip the value of X at coordinate C comma M, you always change the value of G of S comma T because the first term changes while the second term remains unchanged. Therefore, the function G is completely balanced. It's 0 for exactly half of the X's. And the error term we got was the expectation of -1 power G of S comma T. And therefore, this expectation vanishes. So now we are in a good condition because although there were 2 power n plus m many terms in the summation, most of them actually vanish. And we just need to bound the total magnitude of the remaining terms. And to do to consider the case when S is a subset of T. So we again just look at that big expression and write down what the error term looks like. So the error term looks like this. It's the correlation of G with this linear form. So note that, so by G parity S, I mean apply G only to the blocks in S and then multiply them. So this error term is equal to the correlation of this boosted of this tensor function G parity of S with this linear form summation Lj J in T. However, this is just so this is a typo. This is G. So if you look at this expression carefully, this is just a Fourier coefficient of the function G parity of T. So I meant G parity of T here. Sorry, because here you're just this is just exactly the correlation of G parity T with this linear form. So we can upper bound the Fourier the magnitude of this error term by the magnitude of the L infinity Fourier norm of G parity of T, which is simply the L infinity Fourier norm of G power mod T. And we had assumed that all Fourier coefficients of G are extremely small. They were 2 power minus b by 5. So this quantity will be 2 power minus b mod T by 5. And now we are in a position to bound the sum of magnitudes. So we got that P is the probability that we wanted. P minus 1 by 2 power small n plus m is 1 by 2 power small n plus m times all these error terms. And let's group these sums. So let's consider a term where the size of t is k. For each such t, there are at most 2 power k non-zero terms because only S subset of t counts. The other terms just vanish as we saw. And additionally, the magnitude of each of those terms is at most 2 power minus bk by 5 by what we just saw. So there are n choose k many ways to select such a t, which gives this term. For each such t, there are 2 power k many ways to select a s, which gives this second term. And the magnitude of all those terms is at most 2 power minus bk by 5. And in our setting, when b is around 500 log n, you get that this total magnitude is at most n power minus 50. And there is a 1 by 2 power n plus m sitting here. So you get that the total magnitude is 1 by 2 power m times n power minus 50. And this proves our equidistribution lemma. So far, does anyone have any questions? Otherwise, I'll continue to the proof of the conditional Fulling lemma. Okay, so I'll continue. And if you did not follow through, you don't have to worry, because we will be using this as a black box in the rest of our proof. And sorry if I rushed through it, but anyway, we're going to use this as a black box from now on. So here is our original goal. We are given two affine subspaces. We are sampling. Yeah, we have a extendable closure assignment A. We are sampling Z according to mu, and then we sample X to be a uniformly random preimage of Z. And we want to show conditioned on X is in B and X conditioned on X is in A and X consistent with Y. Probability X lies in B is small. And here we are going to use one fact about amortized closure. If you make one more query, the amortized closure increases by at most 1. So to prove the conditional Fulling lemma, it suffices to consider the case where the amortized closure of K is exactly 1 plus the amortized closure of A. Because in the general case, you can consider an intermediate chain of subspaces where the codimension increases by 1 at each step. So now here, this is what we want to show now. If the amortized closure of B is exactly 1 plus the amortized closure of A, then the conditional probability is at most 3 by 4. And now we are going to use one more property. So we're assuming that the codimension of B is exactly 1 more than the codimension of A, and the amortized closure of B is exactly 1 more than the amortized closure of A. In this case, we can actually show that the amortized closure of B will be exactly equal to the amortized closure of A. And this was proven by Efremenko and Itsykson. And this will come in handy soon. So now what we can do is the following. We are given this closure assignment Y. Now let's project this affine space A onto the remaining blocks conditioned on Y. By this I mean the following. Define A sub Y to be the set of all W, which is an assignment to the non-closure variables, such that if you augment W with Y, then that point lies in A. So by the definition of closure, we have that A sub Y is a nice subspace. And we can define B sub Y similarly. And since closure of A and closure of B are exactly the same, A sub Y, B sub Y are both nice subspaces. So now our goal is modified to the following statement. B and A are two safe subspaces. Sorry, I'm interchanging the words nice and safe. Sorry for that. If B and A are two safe subspaces such that the codimension of B is 1 plus the codimension of A, and mu is a distribution on f2 power n, then if you sample Z to be if you sample Z from mu, and then you sample X to be a uniformly random preimage of Z, sorry, this should be Z here, then conditioned on X is in A, the probability that X is in B is at most 3 by 4. And by convexity, we don't have to consider all distributions. We just have to consider a distribution which is concentrated on a single point. So this is our final modified goal, which we are going to prove soon. B is a subset of A. B and A are both safe subspaces, and the codimension of B is exactly 1 more than the codimension of A. Z is an arbitrary point in the unlifted world. So sample X to be a uniformly random preimage of Z. Then conditioned on X lies in A, the probability that X lies in B is at most 3 by 4. And I claim this actually follows almost directly from the equidistribution lemma. And this is the proof. So first we are going to show that probability as you sample x, that x lies in A is very close to 1 by 2 power d. It's 1 plus minus 1 by n power minus 40 times 1 by 2 power d, where d is the codimension of A. And this is easy to follow, easy to see, because let P be the number of pre-images of set in A, and let Q be the total number of pre-images. Now the conditional probability that you want to compute is P by Q. And now by the equidistribution lemma applied on A, we know that P is very close to 1 by 2 power n plus d times the whole affine space. And by the equidistribution lemma applied on the entire affine space, we know that Q is very close to 1 by 2 power n times the size of the entire affine space. So if you want to estimate P by Q, you just use bounds on P and Q separately and you get this result. And similarly, you get a similar expression for B, where since the codimension of B was 1 more, you get D plus 1 instead of D. And now we are done. Because we wanted to show that probability that x lies in A conditioned on x lies in B, probability that x lies in B conditioned on x lies in A is at most 3 by 4. So, well, probability that x lies in A is very close to 1 by 2 power d, and probability x lies in B is very close to 1 by 2 power d plus 1. And the conditional probability is just the ratio of these two expressions. So you just use the upper bound on the numerator and the lower bound on the denominator. And that's it. So this proves the conditional fooling lemma. Sorry if I rushed through it. If anyone has any questions, feel free to ask. And the second part, I had planned to show how we construct this family of hard distributions. And that part is actually pretty big, so I'm going to skip over it. And yeah, this is why I'll end my talk. If anyone wants to go over the construction part, I can go over it. And sorry for rushing through it, but and if anyone wants to ask any questions, please feel free to do so.
Thank you so much, Sreejata. So questions from the audience. I mean, it's getting late in the day and we had a fair number of questions already, but
Well, maybe I can contribute one.
yes, please go ahead.
Yeah, so my understanding is that this construction of the distribution very much depends on the Tseitin formula and on the extender. Is that correct?
Yes, that's correct.
Now, what are some buzzwords you would say about the construction? What ingredients you use?
Right. So we use this classical lemma about right. So we use this following classical observation that has appeared multiple times. So let's say you have a connected graph, and you have these parity constraints at each vertex, so that the summation of the right hand sides is odd. So you have some generic Tseitin formula. Now let's say you're given a vertex V, and suppose you have a spanning tree, and someone gives you an assignment to all the edges not inside the spanning tree. Then you can assign the edges in the spanning tree in a unique manner so that everything other than V is unsatisfied. Everything other than V is satisfied, and only the parity constraint of V is unsatisfied. So what we essentially do...
For any V?
Yeah, sorry, could you repeat that?
When you say V, is that an arbitrary vertex V chosen after I see the spanning tree?
Yeah, no, V is... the spanning tree is fixed. Doesn't matter really. But so here's the statement. G is a connected graph, and there are these parity constraints at each vertex, which are unsatisfiable in summation. You are given any vertex small v and any spanning tree T. Now, someone gives you an assignment to the edges that are not in the spanning tree. Then you can uniquely construct an assignment to the edges in T, so that the parity constraint at every vertex other than V is satisfied, and only the parity constraint at V is unsatisfied. So this is the basic fact that we use. And essentially our distribution is the following. We So we'll just describe this in the case when the partial assignment previously seen is empty, and we just have a connected graph. So the distribution is simply the following. There we fix some spanning tree of the graph. We uniformly at random sample a vertex v, and we sample a uniformly random assignment to all the non-tree edges. And now we assign the tree edges uniquely so that only the parity constraint at v is unsatisfied, everything else is satisfied. This is a natural distribution in my opinion, and the non-trivial part is analyzing it and showing that this is actually hard.
Thank you very much. It's very clear.
Sorry, I cannot hear you, Dimitri.
My question, where do you use Tseitin formula when you analyze by decision tree searching for contradiction? Or no, in this conditional Fulling lemma is not about Tseitin formulas.
Yeah, no. So
Yes.
conditional Fulling lemma is a statement about affine spaces in general.
Yes.
So we want to use the conditional Fulling lemma by so we try to do the random walk with restarts, and so in random walk with restarts at some phase, like let's say at phase j we're at some node, and in the next phase we want to find a deeper node, right? So what we do is that at phase j we are at some node which has a which has a closure assignment which is valid, or as Arkadev said useful. Now, based on that closure assignment, and this part is specific to the citing contradiction, based on that closure assignment, we construct a hard distribution so that if all the prover knows is that you are sampling from this distribution and this closure assignment, then this search problem is very hard for him. We'll consider any such distribution, and then since the prover cannot make progress on this hard distribution, we'll be able to say that we'll be able to find another node at a deeper level. So that part is specific to the citing contradiction. And the equidistribution lemma is used to make the bottleneck argument work. Because previously your paper was using the uniform distribution, and we are saying uniform distribution does work, but any lifted distribution works as well. Because if you have two affine spaces A and B, and at least 1 by s fraction of A lies in B, according where the mass is now counted according to this lifted distribution, then we want to conclude that amortized closure of A increases by at most log of S more than the amortized closure of B.
Thank you.
I hope that was clear.
So, see, it's getting late in the day, and you, Sreejata and Arkadev have already worked for long. I don't know, are there any final questions? Otherwise, maybe we'll start thinking about wrapping up.
I mean, thank you very much for having us and patiently listening to our ramblings.
Our pleasure, I think. So let's give you on behalf of all the listeners, I'll give you a final round of applause. Thank you so much for this tour de force. Thank you.
Thank you for having us.